one thing about writing your own language is the sky's the limit. I mean, you define your own syntax. You decide what that syntax does. Anything you can think of, you can do. Okay, welcome to Writing a Compiler in Go. Now, clearly, this is a 20-minute talk, so there's absolutely no way I'm going to be able to teach you how to write a compiler in Go in 20 minutes. But this is more about what I learned about Go from writing a compiler in Go. So, so I really, the way this started really for me is I wanted to really learn Go, and I was trying to figure out what kind of application would I create, and a compiler seemed to be the thing to do, which would make Go run through its paces. But from what I gathered by what happened, what I really want you guys to get out of this talk is to understand where you can use Go. And the reason is I'm sometimes a little bit worried. I look on job ads for Go and everything, and as we can see from Tom's talk, Go is excellent at networking, concurrency, and as a web app platform. So I get the sense that a lot of people might not realize that Go is actually a very capable systems language. It can do a lot more. It can do a lot of things that you probably ordinarily do in C. And so compiler is one of them. Compiler is about as low latency as you can get. And so this is the challenge here. So by the way, the Coyote there, that's the name of my compiler. I'll show that to you later. But anyway, who am I to tell you all these things? And so let me just give you a little background. Yeah, I've been a developer for 30 plus years. After you get to 30 years, you put a plus after the number. But it's been 32 years. And I've done, in that time, I've done a lot of C, a lot of SQL, a lot of R, and two dots there because there's quite a few languages I was really an expert at that are now dead. Perl and Foxborough and MDX, and they're gone. So, but lately I've been doing a lot of Go and Rust. So I've got something to compare it against. I compared against C, I compared against R, I compared against Python. Anyway, if you guys ever get a chance, it's rainy day outside, whatever, check out my website, intelligences.com. There's some articles on there. There's some nice links on there and so forth. Everything from SQL to data science to so many other things. And of course, after this talk, this compiler that I'm going to share with you is actually available on GitHub, so you can steal it, download it, change the comments so it looks like it's yours, and it's yours. Take it. But anyway, but you get a chance to go through it and everything, and it's I have quite a bit of documentation on it already, so it might be helpful. So anyway, so somebody says, well, what can you write with Go, right? So obviously, like you can write microservices. Again, you go to the job ads and everything. 99.9% of the ads are going to be for microservices, web APIs, etc., that kind of thing. You go on GitHub. You see a lot of small utilities around, and Go is great for that sort of thing. It's easy to get up and running. It's easy to deploy. It makes sense. Now, I don't know if you guys are aware of this. I was kind of surprised when I found this out at first. This is one of the things that made me go towards Go. Was Go is actually used to write some pretty big applications. Docker was written in Go. I mean, you got to figure, Docker is something that's sort of acting like a VM, right? There's no room for lag time or stuff getting slow, right? People won't use it. Kubernetes, which is it orchestrates these Docker images. That's all written in Go. Terraform, I don't know if you guys are familiar with this, but Terraform is a platform that provides on the cloud functions as a service, right? So basically, it's serverless applications. Almost every time that there's a serverless application available on the web, the platform that was used was Terraform, and Terraform itself was written in Go. InfluxDB. InfluxDB is a very fast time series database, specialized database. But in addition to a database, it also has a GUI and charting capabilities for you to be able to chart these time series. The whole thing is written in Go, everything from the database engine to the UI. So so the point is, you need to think big when it comes to Go. Don't be afraid of saying, "Hey, I'm going to create a competitor to SAP." You can do it. It is I guess what I'm trying to say is a lot of people see it as a faster Python, but it's a lot more than that. So I'm hoping to get that across to you when I show you a little bit about my application. Now, sorry about that. See, this is I'm using I'm not using PowerPoint. I'm using LibreOffice, my first time. So, all right. So here we go. All right. So why write a compiler, right? So, of all the things I could have written, why? Well, first of all, it's a huge technical challenge. I mean, anybody who's just getting started is hard, right? I mean, where do you? Now, I wrote one a long time ago. I mean, when I was in school, geez, ages ago, right? And you guys know how long I've been a developer, so you know how long that's been. So I really had to start from scratch and really thinking about how to do this. So it makes it interesting. One thing about writing your own language is the sky's the limit. I mean, you define your own syntax. You decide what that syntax does. If you want to have 8 different kinds of flow control statements, you can. If you want to have functions within functions, you can. In fact, I did that. And so everything's up to you. So you get a certain amount of power. Anything you can think of, you can do. And as it turns out, it's a great way to put a new language you want to learn. It's a great way to put it through its paces, because that's where you really find out where the weaknesses are. Because you can be asking a lot from it. I mean, I certainly did. So here's kind of like the little matrix I used to decide which language versus the other, and so on and so forth. A bit like Tom earlier, concurrency was a big thing, and it's super easy in Go compared to other languages. Okay, it's available in Java and C#. It's they got libraries for that. In C, you have to write hundreds of thousands of lines of code just to get it right. Everything can go wrong. Go, it's simple. So I was kind of tempted by that. Number one for me though was the speed. And I'm going to show you some benchmarks later so you'll see for yourselves. But Go is very fast. Of course, so is C and so is C#. Java, as compared to Go and the others, not so much. But another thing I wanted some data structures in there. Now, you got to consider, if you want to use C, I mean, C doesn't even have strings, right? It certainly doesn't have hash tables. All that stuff you got to build yourself. So, I wanted to piggyback a little bit off of Go's built-in functionality in terms of data structures, in terms of, some functionality. And of course, there's this learning curve thing. Now, I'll put C down as, having a high learning curve. It really doesn't, but C kind of forces you to know a lot of things about the underlying hardware that you don't really need to worry about in Go. So I kind of give it a little check mark there. Java and C#, not that hard to learn, but they have so many libraries, so many things. It takes forever to actually really get very productive on it. And the big thing for me is I want to know runtime. Now, Go compiles to machine code, gives you a standalone executable that you can download and run. A little bit worried about. I know C# offers you sort of that functionality now. You can sort of compile the runtime with the exe, but it's not quite the same. Everything else you have to download a runtime, and I really wanted to avoid that. So as you can see, if you look at this matrix, well, kind of Go clicks all the boxes. So I went with that. Now, there's some other things that came along with it, with the why Go. I mean, if you already know C, which I did, it was very easy to learn. In fact, the folks that designed Go were the same people that designed C. Right? So you can see that when you look at the language, but it has none of the C's hard parts. In other words, in C, you gotta understand how memory is allocated. You gotta understand how to deallocate memory. You gotta really understand pointers, and you have to understand the stack and the heap and understand what's going on. Go just sort of abstracts that away from you, so you don't have to worry about that. It's very hard to make a mistake with memory. And like I said, there's a lot of goodies out of the box. Concurrency, the networking, the data structures, and of course the speed. Now here's some benchmarks. You go to this site. I know it's a long link, but the fact is, if you Google Go versus C performance, you'll get to this site probably. So Go is about half the speed of C++, which is not bad really, because C++ is about as fast as it gets, right? C and C++. So, it's within striking range of C++. is twice as fast as Java, which we all know how popular Java is. It's twice as fast. It's only slightly slower than C#. And keep in mind that C# now compiles to machine code as well, right? But here's what's interesting. It's 100 times faster, according to these benchmarks, than Python. Now, when you think about that, that means kind of like something that's going to take you an hour and a half to 2 hours to run in Python will take you a minute to run in Go. So it's speed is there. Almost anything you can do that you want to do that requires speed, you can use Go for. So anyways, I designed Coyote by my programming language and came up with a little specification. Let me see if I get to it here. You guys can all see that or not? But, so here, I have everything here. I have different data types. It's actually a statically typed language, so you have to define your types. And I have composite types, I have classes, I have enums, I have arrays, I have everything in there, matrices even. And you declare your variables, just like you normally would. It has you could tell it what the type is, but it also can infer what the type is. I have arrays, but I also have multidimensional arrays. And again, going back to this whole thing where, hey, you get to decide how things are going to work. I decided to make the multidimensional array initialization with a little extra sugar in there, telling you what the dimensions of it are inside the definition of the array itself, not in the definition of the variable. So that makes you able now to pass this around as you can make it anonymous. You can pass this expression into a function. I created lists, and then I start playing around. Right? I could put arrays inside a list. So here I got a couple of arrays here of months, and then I can print them out inside this this list. I could have arrays which themselves containing lists, right? So think of a list as a hash map table. So now I got different vegetables here with prices on them. I got meat products with prices on them, and now I can go through and look at the prices of these different stuff that this is just to play around to show you what it can do. I have enums in here. And then I created functions, and I did something here with the functions. I made functions like variables. So that means to say you don't give the function a name directly. You declare the function. I mean, for those of you who've used R, you'll be familiar with this, but I create a function, and the variable itself now contains a function type with the function definition in it. So that means that if I want to run that function now, I just run the variable with the parameters, and I get my value at 4 times 5. But I can also use that function and pass it in as a variable to another function. So I took a very simple contrived example here. I created a function, and all this function does here, if you see it, is call whatever function you pass on to it. And so I created a say hello function, I created a say goodbye function, and I pass these to that function above, and it runs each one of them. So now that makes now this variable, which is a function, I can store it in an array, I can store it in a list, I can pass it back, which is what I do here. So I have a closure. If any of you guys familiar with closures, you can. That means that when you have a function, you can pass it a variable that gets baked into the function definition itself, and then passes back that function with that baked-in definition. So here's a contrived example as well. I have an add function, right? Add something to whatever number you give it. So here I say I'm going to create a function called add 7. What that means is that now I got a function that whatever number you pass on to it, it's going to add 7 to it. And now I create the same function when I give it 10. Now whatever I pass on to G is going to give me that plus 10. Right? So in other words, this number that I've sent here is now baked into the function. So I created a compiler that actually creates functions as first-class citizens, first-class objects. Now, of course, no surprise, we have the regular control flow stuff, switch and case and while and for, and I've added a scan here, right? So, it's a little scanner so for arrays collections, it can just scan right through the collection. Or I can continue, and I made an object oriented. So I've got classes here. So I create a new class, I can create, functions inside the class, I can call these functions, same thing. Now here's an extra twist that I added to the language. I'm still working on this part, but you can create SQL statements right inside the language. So it's inline SQL. In other words, you're not creating a connection to a database and passing in a string, which is the SQL query. You're actually running the query directly as though it were a native command. So it's a little thing that FoxPro way back in the day used to do. No one other language ever did it. I picked it up here. Now the dirty secret here is underneath all of this is SQLite. And SQLite is a local SQL engine database. It has a library and it compiles right into the program. And so for the moment, I'm just using that one. So I'm piggybacking it, but nobody would know. It's all transparent. So anyway, so that's what I set out to do. That's what the language does. Other features I was going to add later on and so on and so forth, but that's the gist of it. Let me see if I run out. I'll run a few toy programs here, just to give you an idea of what this does. So, for example, I have here's a recursive Fibonacci routine. So, let's just run this. Sorry. Can I just run this? Boom. Let's run the wrong one. So that's not the one I want to run. Yeah, sorry. It's had it here. Here we go. So I was too lazy to retype it again, but might have to. And I'm going to call it all right. So here we go. So I ran a recursive Fibonacci routine in 16 milliseconds, and there we go. So it's just a regular application I can write. I can do the same with I don't know. I can do the same with arrays, right? So I run the arrays, so it's oops, never mind. I did have something wrong here. Never mind. Ignore that. So, but anyway, it's let's see if I can run this one. Classes. Yeah, I think I've got something I must have changed in the back, but it doesn't matter. Anyway, you get the idea. So we go back to my recursive and actually see if that still runs. Yep. Okay. So yeah. Let's see why these things don't run anymore. But anyway, so but anyway, you get the idea. I can run a regular program with it. So so how does this work? The compiler basics, the way it works is you have a scanner, and the scanner just reads the code. I'm going to show you some of this code. I'm not going to walk too much through it because it's really large. But let's see if I can just show you a little bit of it. So so the scanner, all it really does, the main thing is it loops over the string that's been sent, which is the program is basically essentially like a string. And what you're doing is the compiler is requesting the next token. So it runs through the strings and it decides what it is. It skips the white space, it checks to see whether it's at the end. It has an alphanumeric, then it runs down and starts running all through the alphanumeric stuff, and so on and so forth. And it keeps giving me back little tokens. So these are keywords, these are variable names, these are numbers, these are strings, whatever it is. It starts sending these back to as tokens, which then the lecture converts into something that has some meaning to it, and then passes it on to the bytecode generator, which is essentially my compiler. And so, so my compiler then, what it does is it goes through all these different tokens and decides what to do with them. And so, so for example, if I want to, let me see if I can find something that's rather simple to understand. So. Yeah, right. So here we have a binary expression. So it came across a binary expression here, a plus or a minus or a times. So it says, okay, great. So now I got a times expression. It's going to decide which one it is. Is it a plus? If it's a plus, let's decide let's figure out what kind of value it is. And if it's an integer value, it's going to do a special kind of addition, especially for integers, one for floats, one for strings, and so on. And then based on that, it's going to emit something. What it emits is bytecode. So in other words, my virtual machine, and I'll show you that in a minute. My virtual machine here is no longer looking at strings. It's looking at individual bytecodes. So what you saw there as I add is really going to be just one byte. And based on that, whatever that one byte is, it's going to know what to do. So let's go and follow that on the VM. So let's get to where it actually adds stuff up. So let's see. So here it is. So it received this command. Now this is a enumerator. So this is just representing one byte. In other words, I sent it a byte and it says, okay, this is the byte that you sent me. My enum, and it's called I add. And based on that, I'm gonna. Now this is a stack-based virtual machine. So what it does is it pops the two integers that I put on top in the stack, and it grabs them, puts them into variables, and it adds them together, and then pushes it back onto the stack. And so but all this is taking place. All this stuff is happening as a result of one byte that was sent to it. So that's what makes a virtual machine a bytecode compiler, kind of like what Java does. That's what Python does. These bytecode compilers, it makes them faster than straight interpreters. And so there you go. So that's kind of the basics of the whole thing. Like I said, this is way too little time to explain the whole thing. It's just a rather large application. But any compiler that you see is going to have these components on them, of one form or another. And so that's what I did with Go. Now here are the good parts that I found when I was doing this. The good part that I really liked was the C-type enumerators. So you remember, like when I had this OP add, well, that's actually an enum, and I was actually able to tell Go that enum represents a byte in order, and it'll actually go from 0 to 255 in order as I declare my enums. And not only that, but what's even better is that it treats them both as equal things. So in other words, I can say, OP add is equal to byte 14. Other languages don't necessarily do that. Rust doesn't do that, for example. I can't do an equality. So it does like C does, and that really was made things a lot easier for me in terms of being able to create this compiler. It's got super fast compile times. Now, why that's good is because when you're making one of these, you're going to be recompiling and checking, recompiling, checking. Oops, and what you don't want to do is wait. Even waiting 10 or 15 seconds each time is brutal. Here, compile times are almost unnoticeable. And one thing here that was really big is array slices. Now, it's about as close as you can get to getting some low-level access to memory. And let me show you what I mean. Let's see if I have. Yeah, so here we go. So I have here a slice. Right? So in other words, I take an array, and listen, I'm just taking an array of these 8 numbers. And let's see if I can run this. Let me just run this off here. Shift F10. All right, so here we go. So as you can see, I initialize a variable called numbers, and I'm going to print it out. So you can see that's all 10. Then I took this thing called a slice. So what I did is I took a subset of that. So that I'm going from the subset 2 all the way to 6, right? So that's going to be 2, 3, 4, 5, 6. And this subslice is going to contain those 5 elements. As you can see here, 2, 3, 4, and 5. So it contains these 4 elements. So forget it because this Go is -1. So I got these 4 elements here, 2, 3, 4, and 5. But what's interesting about this is it's not a copy. It's actually a window into numbers. So here I'm actually going to modify what looks like to me to be index 0, but which is really index 2 in numbers. I changed that to 42. And as you can see, when I print numbers, this one up here, now the 42 is in position 2. Now, now the reason that's so important is because to do that in C, you have to mess with pointers to make sure that you're referencing a window into a portion of the memory space of your stack. Right? What you don't want to do when you get a function call is to create a stack frame, and with that stack frame, you have to create new memory space because that takes too much time. But if I can just get a window into an existing space and treat it as though it's always the positions are always in the same place. And as far as the function is concerned, it doesn't matter. It wouldn't matter where or how big numbers is or where in numbers, what position I'm in. As long as I get my slice, the first one's always going to be 0. So it allows I know this probably doesn't make sense immediately, but suffice it to say, it makes it so that I did not have to initialize new memory every time I call the function. And that saved me a ton of time in terms of my cycles, CPU cycles. This is something that's great that you can do in Go. And so yeah, so this is just I had this here just in case my stuff didn't compile, but and here's the not so good part. Okay, here's the part that I like a little bit less. Okay, the garbage collector is getting a little better. Now, I understand the garbage collector is there to protect you, but here's the problem. It makes this last part up here. It makes the performance a bit unpredictable. So when I had the garbage collector on, and I ran that Fibonacci routine earlier, sometimes it would take 40 milliseconds. Sometimes it would take 80 milliseconds. And why? It's because the way Go, it might have changed a little bit because I know they came out with a new version, but at the time, what it does is it checks to see how much memory you have used up until now. Then it runs a garbage collector. And then the next time, if you've doubled that amount of memory, it runs a garbage collector automatically again. If you double that amount of memory, it runs a garbage collector again. So what then happens is the very beginning, where you're not using that much memory, is running the garbage collector many times, one after the other, until you've actually have a lot more memory in use. So people were doing things like loading up a whole bunch of memory up front just to avoid that, and all sorts of tweaks they had to do. But I thought that was annoying because when you're trying to get as much as you can out of every CPU cycle, the garbage collector is a hindrance. There's no generics. Now, for those of you who used C#, or those of you who used C++, whatever, generics is what makes it possible for you to have one function that can add 2 floats together and 2 integers together based on the data type. Since Go doesn't have that, I actually have to create one function when I want to create, and it does the same thing. It just does A plus B. But if the A and B are integers, I got to create one function. The A and B are floats, I got to create a different function. So it makes you have to kind of create what's a lot of cut and paste type of code, which I wasn't too crazy about. When you're writing an application like this, the fact that you can't control memory allocation is a bit of a problem. It makes it a bit difficult for you to be able to know when you're allocating something on the stack or on the heap. Go doesn't give you any ability to control that. You can hint and try to make it put something on the heap or keep it on the stack, but it doesn't necessarily have to do it. So once again, least unpredictable performance. And of course, no macros. I know I'm running out of time here, so let me just run through this, but let me just say, Go is great for high performance apps is my takeaway. Look, 99.9% of the cases, it's going to be more than fast enough. It's easy to learn, but it still requires some mastery. And that's part that worries me a little bit, because I'm worried that deployers out there think it's just easy to learn, and you're as good as the guy who's done it for 3 years, 4 years, 5 years. You're probably not. There are important things that you can still get much better at Go than the guy who's only been doing it for a year. But it's not so great for optimum performance. I know you guys have a game out there, but if you're going to write a high performance game, maybe not so much. Not for stuff for system languages or embedded stuff, probably Go is probably not good for that. Then again, that's the 0.1% of the 1% of the cases I'm talking about. If you still want to do this, here's a few resources you should probably take a look at. There's a Brighton compiler in Go. I took some ideas from here, not all of them, but it had some good stuff. Language implementation patterns is fantastic. And then there's a website called Crafting Interpreters. I really recommend it. It's great. It's free. You go on there. You can, and the guy did a great job. He wrote a compiler in C, but it really teaches you how to do it. And that's it. Happy compiling.